Okay, so this is the sheet related to your assignments, the Google spreadsheet. I'll share it with you also, Mr. Ramgopal, later on. So here, wherever I've red flagged it, there's some problem with the data set. I might not have gone through all, but these I noticed. Okay, so wherever I see a problem with your data set, I'll red flag it. It just means that I have written some comment that you need to consider, okay, before you go ahead and use this data set. Nothing wrong, because many of you might be doing this for the first time. Some of you might have done it before, so there's no problem. So here I've just told the student Sharanya that the data set that she is using, okay, in this case, I think earlier she was using a different data set. It was GDP data or something like that. And there were only 29 observations. Okay, so it was annual data and only 29 observations. So that's why I red flagged it, because once you take lags or differences, then it's going to get smaller. Even the practical that we are doing, it has 49 observations, and then my training set is dropping to 38 observations. Okay, you'll see what the problems are if you use small data sets. So the larger the better. Okay, and somebody else also here, this time series, I think if you look at the time period, it's 2011 to 2021 annual data. Okay, so this will mean there are just 10 observations. So it's definitely too small for any sort of regression. Okay, so please don't go ahead if you have such a small number of observations. And if these people have not noticed these comments, please draw their attention to it. Okay? It's not a criticism or anything like that. It's just something for you to note so that you can make the changes accordingly. But please don't take it as criticism or anything like that. Yes, Rashi has a question.
Ma'am, I was just asking that can we assume that in between all the datas are correct, or are you still going to check them first?
I will check till tomorrow. It's better all of you enter the data sets by tomorrow. At least choose your data by tomorrow. So update it. Then I'll take a look probably tomorrow night and quickly comment on it. Okay? Or tomorrow evening, because you all might want to work tomorrow. So tomorrow evening by 4 or so, I'll comment on the data sets you have chosen in case I spot any problem. If I haven't commented, you can just go ahead.
Sure, ma'am. By the way, I have already uploaded it, but it's okay. I'll wait till tomorrow. Thank you, ma'am.
Okay. And one more thing, annual data will not have seasonality. Okay, the seasonal patterns, they just get averaged out, so you will not need to do any sort of seasonal adjustment. I'll come back to the assignment towards the end of the class, and we'll discuss a little more about the specific things that you need to note for your assignment itself.
Ma'am, just one question. I just joined now.
Yes.
I'm Sharanya. So,
Yeah.
ma'am, you told that my data is short. So today morning I have changed my data set. I'm now taking interest rates of long-term interest rates for 5 years, and it's monthly data. Will that work from 2016 to 2020? Long-term interest rates, and it's
Yes.
monthly data.
Yes, that should be fine. You'll have 60
Okay.
observations, right?
Yeah, and
Okay.
like 2021 is 69 observations.
Okay, fine. Yeah, that's good. You can go
Okay.
ahead.
Okay, ma'am, that's what
Yeah,
I
I'll
wanted
delete
to know.
my comment later. Don't worry too much
No, it's
about
okay. It's okay. That's not a problem.
that. Fine, let's just come back to the practical that we were doing yesterday. Okay, so I'll just run some of these commands. You all are following along, right? Okay, I'll just wait till you all also update. I didn't enter my data set. Okay, so that's why there's a problem. Are you all following along or you all are just watching? Yes, are you all following or you all will just be watching? Because if you all are just watching, then I can go a little faster.
Ma'am, can you share this? Can you share this file?
Can you all see this? Is this visible to you all?
Yes, ma'am.
Okay, I won't be doing all these unit root tests again. Okay, so I'll skip that part. I'll just do the new set of unit root tests. All right. So are you all ready? Can I proceed? Yes, can I go ahead with the unit root test or you all want me to wait?
Ma'am, could you please copy paste the codes?
Where exactly do you want me to copy paste it? In the
Google
chat
chat.
window,
Yeah,
is
yeah.
it? Okay. Okay, so I'll do it from here. Okay, you will have to enter the data set in yourself. Just use this import data set wherever you have stored your data set. Okay, from Excel, wherever you have stored it. Meanwhile, I'll just copy paste this. Wait. Since I was selecting, I'll do it from here, okay? Since I'm not entering all this code, so I'm not selecting it from the script. Okay, you'll have to remove this part over here to be able to use the code. Okay, just let me know once you're ready and then I can start. You have to load all those packages, okay? Otherwise it might not run the commands. I'll just paste that also for you. Okay, please let me know once you're ready. If you're just watching, then I can proceed. Can I begin? Okay, can I start, yes or no?
Yes, ma'am.
And we'll just do one more test, all right? This is the ADF test. So since I've already done 3 versions of the ADF test, I'm just calling this DF4, okay? So this is from the package funit roots, okay? This is slightly different from the others. This is the last unit root test that we'll be doing. After this, we'll move ahead. Okay, so the command here is Adf Test. Okay. Now, if you look at the prompt, okay, in this you'll specify the name of the time series, which is SAR. That's what we are interested in. Then again, you'll have to specify the type of test that you want to run. For example, do you want to include a trend component or just the drift, okay, or no constant, no trend. Okay. So here, this is the one I'm looking at, Adf test. Okay, so I first want to run the model with the trend and the constant. So I'll choose type equals CT. Okay. And then I have to specify the lags in this test. Okay, so there's no shortcut or there's no formula which is inbuilt by R to actually select the number of lags in this test. Okay, so I'll just select one lag for now. And then so I'll just run this command and see what the result is. So here you can see this is the critical value, the value of the test statistic itself, and the p-value is quite low. Okay, so basically from the p-value you'll understand that you need to reject the null hypothesis here. So you're rejecting the null hypothesis of a unit root and you're accepting the alternative that the time series is stationary. Okay. Here I think I'd saved the results somewhere. Yeah. Okay, so I'm just saving the result for my reference. So here I'm rejecting the null, okay, and concluding that the time series is stationary. Okay. Now let me just check, since I suspected some kind of a drift in the model, let me just check by changing the type of test from trend constant to just constant. Okay, let's see if that makes any sort of difference. Okay, now I'll just print the results again for this. So here again, I'm rejecting the null. Okay, at the 5% significance level, I'm able to reject the null, 5 and 10%. Okay. So in the case of the model with trend and model with drift. Okay. In this case also, I'm rejecting the null and concluding that the time series is stationary. Okay, so basically, I've done a battery of tests so far using different packages, the Adf test, Phillips-Perron test, and the KPSS test. So most of them concluded that the time series was stationary. Okay, but there were just a couple of tests which told me that the time series is actually non-stationary. For example, here in the model with drift, when I used this package, and I used the model with drift, the Adf test was telling me that this time series is non-stationary, okay, because I failed to reject the null at 1%. So basically, this is quite an important result, because if I use multiple samples from this data generating process, what this result is telling me that in only one time out of 100 times that I do this sort of an exercise, will I be wrong about this result, which is that the time series will actually be stationary. So here this result is telling me that 99 times out of 100, if I repeat this sort of an exercise, I'll find that the time series is actually non-stationary. Okay, so this might be significant. I might give a lot of weightage to this. Okay. Then here also, in this Adf test using the T-series package, okay, again I failed to reject the null. I found that the time series was non-stationary. Okay. Even in this KPSS test, again from the T-series package, I found that the time series is non-stationary. Okay. So depends on which of these I'm giving a lot of weight to. Okay. So we'll try both sets of models. one where we are differencing the time series to make it stationary, and one where we are concluding that it's stationary and then proceeding with it. Okay. So here, if you all want to actually do it along with me, let me know. I'll go a little slower. Otherwise, I'll just keep typing out the commands and you all can follow along. Okay. So first, let's begin by actually differencing the time series. Okay. So I'll call this dr1. I'm going to take the first difference of this variable. Okay. Now let me just plot this variable. Okay, now this appears to be stationary. There's no downward trend over here. Okay, although the variance is fluctuating a bit in this portion, okay, even over here, but it looks more stationary compared to the previous graph. Okay, so let me just quickly check again whether it's stationary or not. So here I'm going to test dr1 to see whether it's stationary or not. Here I'll check whether it is stationary as it is. Okay, so I'll use the command null hypothesis level. I'm checking whether the time series is stationary as it is, okay, after I have taken the first difference. And then let me just run this. Okay. So here you can see from the p-value that I'm finding that the time series is stationary. I'm not able to reject the null hypothesis of the KPSS test. Okay, so differencing this time series has made it stationary. Okay. Now I'm not going to repeat all the other tests, but since I had that suspicion, I've checked using the difference data. Okay, so first what I'll do is I'll model assuming that the time series is stationary because most of the tests reach that conclusion. Okay, and then I'll model using the conclusion that I feel is right, that the time series may be non-stationary. Okay, and then we'll compare the two. So here, let me start by just using this command first. Okay, so this will allow me to plot the time series as it is, the ACF and the PACF. Okay. So here, if I look more closely at this is the original train 1 data, which we seasonally adjusted, that's SAR, okay, SAR. Now, if I look at the ACF, it will help me determine the MA order of the process of the time series. And if I look at the PACF, I'll be able to determine the AR order of the time series. So just looking at this graph, can anyone tell me what order I should select to begin the whole modeling exercise for Arima modeling? Anyone can take a guess. Okay, how will you determine the MA order? The autocorrelations will begin to decline after or decay after lag Q. Okay, so that will help you to determine the MA order of the series. For the AR order, the autocorrelations will begin to decline after lag T. Anybody?
So we may take 3 with the help of ACF.
Okay, from the ACF, you will choose the MA order as 3. What about the PACF?
I think 3 again.
Yeah, 3 again. Okay. So let's begin with that. So let's call this mod 1. So the time series that we want to model is SAR. Then we'll select the order of the model. Okay, you're specifying the MA order, AR order, and so on. So here, since I'm going with the majority result or consensus result from all those tests that the time series is stationary. I'm not going to difference it in any way. Okay, so that's why the order is 303. Then I need not include any seasonal component since I've seasonally adjusted my time series already. Okay? So we'll just run this command as it is. Okay? After this, you can look at the results using summary mod 1, and you can also do the diagnostic checks using this command. Okay? 1. So I'll just select these two and run the command. Okay, so here if you look at the results from this, okay, which of the coefficients are significant out of these?
Again, we have to check in respect to that key value that we did earlier.
Yes, here you'll look at the absolute value. If it's greater than 2, you'll conclude that the t value, the coefficient is significant. Okay. It's a two-tailed test here. You're checking whether, for example, the AR1 coefficient, your null hypothesis is that it's equal to 0. Alternative is that it is not equal to 0. That's why it's a two-tailed test. Okay, basically, you're checking whether that coefficient should be there in your model or not, or should you drop it.
So basically, MA2 is not significant.
Okay, MA2 is not significant. What about the rest? I think almost all are not significant. Okay, except for the mean here. I think all are not significant. Okay, now let's just save the AIC from the model. Okay. I'm just writing that. If anyone finds that any of the other coefficients is significant, just let me know. But I don't think so. Okay, then if you check the results from this test, I'll just come back to this in a minute. You look at this plot, you can see that there are no significant autocorrelations in the residuals. If you look at the ACF of the residuals, there are no significant autocorrelations. So you know that the residuals look fine. They look like white noise. Then they appear to be normally distributed, okay, and have a mean value of 0. Then to interpret the Loom Box test, the null hypothesis of this test is that the squared autocorrelations, okay, a group of squared autocorrelations, the null hypothesis is that these squared autocorrelations, the sum of these squared autocorrelations is equal to 0. Okay, and the alternative is that it's not equal to 0. So here, basically you're trying to determine whether there is any sort of autocorrelation amongst the residuals, because if there is autocorrelation amongst the residuals, remember that any white noise residuals, they're supposed to have 0 autocorrelation amongst themselves. So if that condition is violated and the residuals are actually autocorrelated, it means that there's some information left over in your data set that you did not use adequately. Okay? Probably that you haven't included the right coefficients in your model or something like that. Maybe your model is misspecified or there's some sort of a mistake in your model. So you probably need to go back and check your model again, estimate a different model after making some changes. So that is how you will interpret this test result. I think Mr. Ramgopal, you had a question about this, right?
Yes, ma'am.
Okay. Is it clear to you now?
I guess it's better, but still
Okay.
I need to think about this slide.
Okay, just remember that for white noise, any white noise time series, one of the properties of such a time series is that the time series will not be autocorrelated.
Okay, fine. This is testing for autocorrelation among residuals, right? Basically,
Yes.
that. Yeah, okay.
So after you note down the AIC, then you can just say diagnostic check is fine. Okay. Everything seems to be fine when it comes to the diagnostic checks. Okay. So since most of the coefficients were insignificant, we can just probably drop maybe one of the coefficients and re-estimate our model. Since we want a better model, we want a model with at least some coefficients being significant. Okay, so let's try and estimate again. So instead of using 303, let's just tweak it a little and change it to maybe 302. Okay, we are changing the MA order here. So whenever you find that one model is not fine, you just need to change the specification slightly, maybe drop one MA coefficient or one AR coefficient and then proceed that way. Okay, so we'll just do this. We'll change the name of the model to mod 2 and then go ahead and need to run all these commands. Okay, so what you'll notice now is that AR1 is still insignificant, AR2 is insignificant, AR3 seems to be significant here. Okay, MA1 is insignificant, MA2 is insignificant, the mean is significant. Okay, so only AR3 seems to be significant here in our model. Okay, let me just quickly check that. Okay, when it comes to the AIC, it has dropped further. If you look at the AIC compared to the previous model, so we know that we are moving in the right direction. Okay, then if you look at the Loom Box Test results, there doesn't seem to be any sort of residual autocorrelation. Even the ACF is telling you the same thing. Okay, and the errors seem to be normally distributed. So diagnostic check wise, we are doing fine. Okay, let me just quickly check the significance of that particular coefficient. Okay, so I'll just save my results again. Let me just paste the AIC.
Ma'am, for AR3,
Diagnostic checks appear to be fine, yes.
ma'am, for AR3, I'm getting the value 1.98.
Yeah, that is marginally significant. You can consider it, okay?
Okay.
You can just round it off to 2, so it's marginally significant. It's a very marginal thing. Okay? I'll just add that comment here. Okay? So again, let's tweak the model. Okay? Since most of the coefficients are turning out to be insignificant, let's just tweak it again. Okay? This time I'll drop one AR coefficient, change this to model 3, and then run this set of commands. Okay, so again, diagnostic check wise, you can see it seems to be fine. Everything seems fine. AIC has dropped further. Okay, now let's look at the result. So this time AR1 is significant, AR2 is insignificant. Okay, MA1 is significant this time, MA2 is insignificant, and the mean is significant. Okay. So AR1 and MA1 are significant and the mean is significant. Okay, here I need to add that the mean is significant. So here AR1, MA1 and mean, okay, are significant. So AR1, MA1 are significant and the mean is significant. Then let me just save the AIC result and state that diagnostic check wise everything looks fine. The residuals are not autocorrelated based on the Loom Box Test result and also based on the ACF, and the errors seem to be normally distributed. Okay, so this seems to be the right model. Let me check again. Okay, by estimating this time, Arima 101. Let's try that this time, since that seems to be a better specification. So I'm changing this to mod 4 and the order to 101 this time. So this time if you look at the results, okay, what you will find is the AR1 coefficient is significant, MA1 is significant, even the mean is significant. AIC has dropped further. Okay, so this is the minimum value that we've got so far out of all the models. Even Loom Box Test, it seems fine. Okay, so diagnostic checks wise also everything seems fine. So I think we can stick with this model. Let me just save the results here. Sorry. Okay, this time it's 175.39. This comment is related to the previous model, model 3. Okay, and this is related to the fourth model that we estimated. So since everything seems fine, let's just stick with this model itself, okay, for now. So I'll just add another comment here for my reference. Okay, so model 4 is giving us the best fit, or it's the best performing model so far. Okay, so let's stick with this and I'll quickly estimate the model for the different series. Okay, so just bear with me for a few minutes. I'll quickly estimate the model for the different series, then we can compare the two. Okay. So for the different series, what I need to plot is DR1, okay, where I differenced SAR1 to taken the first difference of SAR1. So let me just run this command. Okay, so now if you look at this plot, this looks somewhat different. Okay, before we come to this, I think Mr. Ramgopal was earlier pointing out that it might be a near unit root case, okay, which is what we see in this case. For model 4, if you look at the coefficient of AR1, it is almost 0.95, right? Okay, so this might be the problem. This is why I might be suspecting that it needs to be differenced. because it's a near unit root process. Okay, but still, just for my own satisfaction, let me fit a model with a difference series and then compare the two. Okay. So here, if you look at the ACF and the PACF, okay. Can anyone tell me what model they'll select this time?
MA of lag 1 and
Yeah.
1 or 2 or
201.
Yeah,
So
2.
that's 0, right, okay.
Okay. Since here the decay is beginning after lag 2, that's why you'll select lag 2, okay, for the AR order. And since we are looking at the difference series, when we are fitting the model, it will become 2, 1, 1. Oh, sorry, 1, yeah, 2, 1, 1. Okay, 1 lag from the MA order and 2 lags for the AR order. Okay. So let's just try and fit that model. I'll just call this D mod 1, okay, to indicate that I'm interested in the difference series here. So again, I'll use the Arima command. This is with a capital A. Okay. So again, I'll put SAR here. Okay. You will not put the differenced variable here because the model itself will do the differencing of the variable. Okay. So you can specify that you want a first difference in the order itself. So we said 2, 1, 1. Okay. So that is the order we'll select. Then I'll just check the results. Okay. This will save you time when you're writing your own script, all right? If you just copy paste the commands. Okay, so in this case, what you find with this model is, if you look at the AR1 coefficient, is it significant? AR2 is, I think, not significant. MA1 is significant. Let me just check.
Now only MA1 is significant.
Yeah, MA1 is significant. The rest are not, right? 0. Yeah. Okay, so only MA1 is significant. What about the other things? Like AIC is 169.2. Then Loom Box Test, that appears to be fine. So we'll just save these comments. Okay, so only MA1 is significant. Then I'll just paste the AIC. And diagnostic checks, if you look at it, it appears fine. Okay. No residual autocorrelation from based on the ACF plus the Loom Box test results, and errors appear to be normally distributed again. Okay, so instead of this, since both the coefficients, AR coefficients are insignificant, let's just try dropping 1 and see what happens. Okay. Oh wait, sorry, this diagnostic check was for mod 1, not D mod 1. Okay, but yeah, the same result is there. Okay. So let's just paste these commands again and tweak it a little. So this time I'll put 111, change the name of the model to D mod 2. Okay, so let's just look at the results. So this time AR1 is insignificant, MA1 is still significant. Okay? AIC has dropped further. So this seems to be a better model, but we'll probably need to drop the AR1 coefficient entirely. Okay, no AR coefficients at all. Diagnostic checks wise, it appears to be fine. Okay, so let me just save these comments again. BC is fine, diagnostic checks, everything appears to be fine. So let's just drop this coefficient entirely, the AR coefficient, and estimate just an MA model. Okay. So here it will have to be 0, 1, 1. Okay. Change the model name. Okay, and I'll run this entire set of commands. Okay, diagnostic checks wise, everything appears to be fine. AIC has dropped further, MA coefficient is significant. So this time it's a very, very parsimonious model that we are selecting. I'll just paste it from here. So this is our best fitting model, Arima 011. Okay, in this case. This is best fit based on AIC, okay, since we haven't done any sort of forecasting or anything like that. Now earlier we had selected, I think, mod 4. Yeah, so what is mod 4? It is Arima Z101. Okay, I'll just save that also here. Okay, now let's just see if we had chosen auto Arima instead of going through this whole process by ourselves. If we had just chosen auto Arima and run the command, what result would R have given us? Okay, so here you don't even have to bother about whether you're considering differencing or not. R will do or select the model for you. Okay, so we'll just call this. Let's call it A mod 1. Okay. Let's call it AA mod 1 to indicate that it's auto Arima. Okay. So you just have to put in SAR, the name of the variable that you are interested in modeling, and tell R that it is not seasonal data since we've already seasonally adjusted it. Okay, so you'll put seasonal equals false and run this command. Okay. Yeah. So diagnostic checks, everything appears fine. So R has also selected the 011, okay, model. Did we select that? Yes. Okay. So R has selected the same model as us when we used differencing or took the first difference of the variable. Okay. Now after this, let's just take a quick break for 5 minutes and then we'll discuss the forecasting part of the entire exercise. All right. Let's just break for 5 minutes. We'll meet at 3:35. All right, hope you all are back. It's 3:35. Any doubts or questions so far? Okay, fine.
Hello, ma'am, 1 second.
Yes.
Yeah, this data of SAR is adjusted for seasonality, but when I was just viewing the data, it looks the same as that other one, the train
Yes.
one data.
Yes.
So essentially, it did no adjustment, which is
Yes.
what we thought yesterday, right?
Yes.
Okay.
So when we used X13, it didn't detect any sort of seasonal pattern. I'll just quickly show you here. If we just do this for RPI. Wait. This is for the original data. So this is the index itself, not the returns. You can see these perfect circles, right? So there does not seem to be any sort of seasonality in the actual data. If you look at the RPI data itself, since you're getting perfect circles here, maybe there was no seasonality at all to detect. So maybe that's the reason why there was no seasonal adjustment which actually took place even when we used the X13 command. X11 still did some kind of adjustment, but X13 did not. Okay, X13 seats.
So we will get the same result if you run an auto Arima on the original data with seasonal as true.
I don't know. We'll have to try it and see.
Okay,
Wait,
thanks.
let me just try it. Original data, is it you're saying? You mean RPI or the returns?
No, the train one, right? That
Train one, okay.
Yeah.
Train one. I don't know, but let's find out. I will check the summary and no, here it has added a seasonal MA component. So here there's a fourth lag is probably significant somewhere. This is the residual plot, so we'll have to look at the actual plot of the data. Let me just see. So here at the fourth lag, there's no significant spike here. So I don't know exactly why Auto Arima has selected this. There should have been a significant spike, but there isn't. And Auto Arima you can actually beat Auto Arima sometimes. It's not always the perfect answer. So maybe our model is better. I really don't know. I'll just run these set of commands again because I want. Okay, actually I need not because it's the same model as D mod 3. Okay, so I'll just use those results later on. So let's just, before we actually do the practical part of the forecasting, I'll quickly take you through a little bit of theory. Okay, it won't last long. These are short notes. So if you consider an AR1 model, you might want to forecast one period ahead. Okay? So if your sample ends at, let's say, time t, then you might want to forecast for the next period. And in that case, if you know the value of these coefficients, A0 and A1, then you can forecast the value of yt plus 1 conditional on all the information available at time t. Okay. So you can find out what will be the expected value of yt plus 1. If you take expectations of these, expectation of et or epsilon t plus 1 will be equal to 0. So you end up with this equation, equation number 3. Now similarly, if you want to find out what is yt plus 2, if you want to forecast 2 periods ahead, then the forecast will be based on yt plus 1 here, since that is the previous value that you have for this particular time series. So to find out what your forecast will be, you will be taking or finding out what is the expected value of yt plus 2. Since expectation of epsilon t plus 2 is equal to 0, this term will drop out. And here you will have expectation of yt plus 2 is equal to a naught plus a1 expectation of yt plus 1. So you will be forecasting the value of yt plus 2 based on the forecast of yt plus 1. Okay, the value that you forecasted for yt plus 1. Now instead of expectation yt plus 1, we can just put this part in from equation 3. So then we get equation 6. Okay. So if we keep iterating forward this way, if we generate forecast for yt plus 3, 4 and so on, then the forecast of yt plus 1 can be used to forecast several periods forward. Okay. So in general, if you keep iterating forward, then you can find out what will be the value of yt plus j plus 1. You can generate forecast for the time period t plus j plus 1 based on the forecast for yt plus j. Okay. So here in this equation, if you keep substituting, okay, for example, for expectation yt plus 2, we substituted from equation 3, our expectation of yt plus 1, and we got equation 6. So similarly, if you keep substituting this way on the right hand side, finally you will be able to get the entire sequence of j step ahead forecasts using the process of forward iteration. Okay. So in the place of expectation yt plus j minus 1, you will be able to substitute and write this entire sequence over here. Okay. And this will be the initial value. Just before you started forecasting, what was the value of yt? Okay. So now if you look at this seems very familiar, right? This is something that you'll have come across when you are solving difference equations. So you can consider this to be some sort of a solution to a difference equation here. Okay. Now equation 8 here expresses all of the j step ahead forecasts as a function of the information available at time t. That's why we have this subscript here, expectation at time t. So you're generating your forecast using all the information available up to the end of your training data set or the sample that you've selected. For example, when we are doing our practical, we've selected data up to 2018 quarter 4. Okay. So when you're generating your forecast, you'll be using all the information available until 2018 quarter 4, starting from the beginning of your time series until 2018 quarter 4. So all the information that's there in the data set will be used to generate these forecasts. Now, if you consider equation 7, okay, this equation as a first order difference equation in the ET, YT plus J sequence. Okay. Now, remember that when we are looking at solving first order difference equations, in order to make sure that our time series was stationary, we used to assume that A1 is less than 1. The absolute value of A1 is less than 1. So here also, we want our time series to be stationary, and then we go ahead and model and generate forecasts. Okay. So since you know that A1 is going to be less than 1 in terms of its absolute value, in the limit, this forecast of YT plus J, okay, that you are generating, it will converge to the unconditional mean of the time series. So this is what is written in the next line. So for any stationary Arima model, the conditional forecast of yt plus j. Conditional forecast means conditional on all the information available up to time t. So in our case, for this practical, up to 2018 quarter 4. So the conditional forecast of yt plus j converges to the unconditional mean as j tends to infinity, or the forecast horizon tends to infinity. For example, in our case, I wanted to forecast 9 quarters ahead. That's why I left out the last 9 observations. But suppose I want to forecast for infinite periods ahead, then finally my forecast for j tending to infinity, it will converge to the unconditional mean of this time series. Okay, but we never actually forecast that far ahead in time. We generate short-term forecasts and then discuss those. Now in practice, if we consider the j step ahead forecast, okay, forecast error. So how will you find the forecast error? So this is the j step ahead forecast error, which you generate based on information available up to time t. That's why this subscript is there. Okay. So you'll find out the forecast error by taking the actual value of the time series at time t plus j minus the forecasted value, the value that you have forecast for the time series at time t plus j. So that will give you the forecast error. For example, the one step ahead forecast error will be the value of the time series at time t plus 1 minus the forecast that you generated for the time series at time t plus 1. Okay. So if you look at the previous equation here from the previous page, okay, so if you take expectation here of yt plus 1, okay, then expect yt minus expectation of yt plus 1 will be nothing but et plus 1, because if you take expectation of yt plus 1, you'll just get this term. Okay. So that's what has been written here. Okay. So this is nothing but a naught minus a1 yt, that will be coming here. So you're left with epsilon t plus 1. Okay. Then similarly, the forecast error, okay, in the second time period, or the second forecast error that you make, okay, will be equal to the difference between the actual value of the time series at time t plus 2 and the forecast that you generated for the time t plus 2. Okay. So if you keep substituting the same way, okay, so this here is nothing but yt plus 2 minus expectation of yt plus 2. So from here, instead of yt plus 2, you can plug in this part. Okay. Then you can find out what is expectation of yt plus 2 from equation 5. So the difference between the two will give you this equation here. Okay. Et plus 2 plus a1 epsilon t plus 1. Okay. This is epsilon. Since I have et here, I am referring to this as epsilon t plus 1. So for any AR1 model, you can write the j step ahead forecast error this way. Okay, so it will be a sum of the errors or the residuals from your time series, or the true forecast errors basically. Now since the expectation of et plus j, the expectation of the j step ahead forecast error will be equal to 0. Okay, since expectation of epsilon t plus j is equal to 0, even this, the expectation of this is also equal to 0. So the expectation of your forecast errors, j step ahead forecast errors, will actually be equal to 0, or basically the mean of your forecast errors will be equal to 0, which means that your forecasts are unbiased estimates of each value of yt plus j. Okay. So you'll be getting an unbiased estimate of the true value of the time series, okay, if you're generating the forecast. then although unbiased, you will find that the forecasts are generally inaccurate, because if you remember, the variance of this ET plus J, or the forecast error, it's not equal to 0. Okay? Instead, it's equal to sigma square. So if you take this equation again, and if you find the variance of the way step ahead forecast errors using this equation, okay, if you're forecasting 1 step ahead, the variance of your forecast error will be equal to sigma square. If you're forecasting 2 steps ahead, it will be equal to sigma square plus A1 square sigma square. So similarly, if you're forecasting J steps ahead, you'll find that the variance keeps increasing, okay, according to this formula itself. So you'll find that the variance of the forecast error is an increasing function of J, or your forecast horizon. So the further out into the future that you forecast, the more uncertain your forecast will be. Okay? You cannot be very confident about your forecast, maybe 20 periods ahead. You can be more confident about your forecast maybe 10 periods ahead. Okay? So the further out into the future you forecast, okay, there will be greater uncertainty or variance associated with the forecast error. Okay? So as J tends to infinity, you will find that in the limit, the variance of the forecast error will converge to the unconditional mean of the YT sequence itself. So the basic idea that you need to understand from here is that you can have greater confidence in short-term forecasts compared to long-term forecasts. Okay, so if you're forecasting using quarterly data, maybe 8 periods ahead or 12 periods ahead, you can be more confident about those forecasts compared to if you're forecasting maybe 36 periods ahead or 24 periods ahead. Okay? So the first few forecasts will be more certain compared to the later forecasts that you're generating. Okay? Now in practice, we don't know the actual values of the time series. We're working with a particular sample of the data generating process, right? So because of this, since you're working with a sample, you'll have the actual value of the time series from your sample at time t plus 1. Okay? So think of t as the last observation that you use to model. So in our case, the observation related to 2018 quarter 4. Okay? So this is basically 2019 quarter 1. Okay? This is the value of the return series for 2019 quarter 1. Now to find the forecast error itself, you will find the difference between the value of the time series at time t plus 1 and the value that you predicted for that particular time series or forecast for the time series. Okay, so how will you make your forecast? It will be based on the previous value available to you. Okay, so here YT here refers to the value of the return series at time 2018 quarter 4 here. Okay. So once you've estimated the coefficients from your Arima model, for example, if you had fit a simple AR1 model, you would have had some estimated value of the constant or the intercept term and some estimated value for the AR1 coefficient. So you will plug in those and then find out what is the value of your forecast error. Okay. Now there are different methods that we use for forecasting. Okay. So you have something known as the average method. So basically, these are all referred to as benchmark methods. So you will be comparing the forecast that you generate from your model with these benchmark forecasts. Okay, so when you forecast using the average method, each of your forecasts, for example, if I'm forecasting forward from 2018 quarter 4, so all my forecasts will basically be equal to the mean of the time series. Okay, so it will be equal to the mean of train 1 or my training data set here. So there won't be any sort of variance in the forecast. All the forecasts for 1 step ahead, 2 steps ahead and so on, all of them will be equal to the mean or the average of the historical data or time series. Okay. So this is the average method. Then you have something known as the naive method. Okay. So basically in the naive method, you're going to set all your forecast to the value of the last observation that you have. Okay? So this is very similar to the random walk model that we were discussing. So your best guess for today's price of a stock, for example, would be yesterday's price. So similarly, your best forecast for one period ahead would be the previous value available to you. Okay, so the last observation that you have available to you, that will become your forecast for the period ahead. Okay, then if you want to forecast 2 periods ahead, since you'll be basing it on your first forecast, again it will be equal to the last observation that is available to you in your data set. Okay? So these are known as random walk forecasts because they are very similar to the logic of the random walk model itself. Okay? So this is also called the naive method or the random walk forecast. Then you have something known as the seasonal naive method. So you'll be using this for data which shows a lot of seasonality or has very strong seasonal patterns. So here each forecast will be equal to the last observed value for the same season of the year. Okay? For example, if I'm forecasting the value for the first, suppose our data that we are using now was seasonal or showing very strong seasonal patterns, then if I was forecasting for the first quarter of 2019, okay, my forecast for the first quarter of 2019 would be equal to the last observed value from the same season of the year. Okay, since the last observed value from the same season of the year that I have in my data set is the data for 2018 quarter 1. Okay, so my forecast for 2019 quarter 1 will be equal to the value of the time series for 2018 quarter 1. Okay. Or if I'm taking monthly data, for example, so if I'm forecasting for, let's say, October 2021, and I have data until maybe 2020, and I've used that to generate my forecast. So my forecast for October 2021 will be equal to the value that was there for the time series for October 2020. Okay, so this is a seasonal naive method. The forecast will simply be equal to the last observed value from the same season of the year. Okay. You will not have to actually calculate all this, okay, but you can go through this formula later on. If you plug in some numbers here, you'll be able to understand what it means. Okay. Now the forecast error itself, when you're actually dealing with data, when you're doing empirical work, it will be equal to the difference between the observed value and its forecast. Okay, so far what we were talking about was related to the population or the data generating process. Okay, if you're forecasting based on that, all this that we were talking about here. Now, once you actually get a sample and you're working with that, then your forecast error will be equal to the value of the time series at time t plus h and your forecasted value at time t plus h, okay, conditional on all the information available up to time t. After this, we'll just generate some forecasts and then I'll come back to this, okay. So I think you all might understand this. In case you're a little confused, you all might understand this better once we actually generate the forecast. So let's just go ahead and do that. Okay. So first, I'll just create my test data set. Okay, I want to compare with my forecast with the actual data. So I'll just create my test data set. So here you'll use the command window again, because you're extracting one particular part of your time series. So here window R1, which is the return series. Okay, since no seasonal adjustment took place here, so I can just use R1 directly. Okay, there won't be any problem here if I use R1 directly. Okay, so one thing that I want to point out here is we seasonally adjusted only train 1, okay, but this was okay in this case because X13 seats did not actually carry out any sort of seasonal adjustment. So it's okay. Yeah. But if you are doing this sort of taking a subsample within your sample, then seasonally adjust your entire data set and then create train one and test one. Okay. So here, for me, test one is starting from the first quarter of 2019. I need not specify where it will end. R will be able to figure that out. Let me just run this command. So R has created test one. So I left out 9 observations so that I can compare my forecast with these 9 observations of actual data. Okay. So now let's generate the forecast. Just stop me at any point if you have any questions. Okay. So to generate the forecast, you'll use the command forecast and then whichever model you want to generate the forecast for. Okay, so here I want to generate forecast for D mod 3. Okay, once you've done that, then specify the forecast horizon. Okay, so suppose I want to forecast only one period ahead. Okay, then I'll select one. If I want to forecast so that I can compare with my entire test set here, then I'll forecast 9 periods ahead since I have 9 observations in my test set. So basically I'm generating 9 step ahead forecasts here. Okay. So let me run this command. Okay, now you can just check what F1 is actually. So run this command. So once you get to see this, okay, what you'll see is this is the forecast for the time series. Okay, so you're forecasting the returns in several periods ahead. Okay, in this case, all seem to be the same. Okay, there seems to be no difference in the forecast at all. Then if you look at this part, okay, so this is a confidence interval. So it's an 80% confidence interval, which basically means I expect the true value of the return series at time 2019 Q1 to lie within this interval with 80% confidence. Okay. Or this is the specified probability with which I expect the true value of the time series to lie within this interval. Okay. Similarly, this is the 95% confidence interval. Okay. If you look at this, so again here I'm expecting the true value of the time series to lie within this interval, which is specified here, between minus 2.43 and 5.70. Okay, I expect it to lie within this interval with 95% confidence or a probability of 0.95. Okay. So let's just plot the forecast, then you'll be able to maybe understand better. Okay, so let me run this command. Okay. So this is what our forecast looked like here. So you can see it's a straight line. There is no variation in the forecast at all. Okay. And this here, if you look at the darker shaded region, this is your 95% confidence interval. Okay. The lighter shaded region, this entire region is the 80% confidence interval for your forecast. Okay. Any doubts or questions at this point?
I didn't understand the significance of this blue part, the confidence interval part.
Okay. See, for any coefficient, you would have learned when you're studying basic econometrics, right? How do you create a confidence interval? I'll just type it here in the chat box.
Ma'am, I got this, but I'm not understanding what is presenting through this image.
Through the graph, okay.
Yes, through the graph.
So you know how to create confidence intervals?
Yes, ma'am.
Okay. So basically, this is showing how much uncertainty is associated with your forecast. Okay, so you're saying this is my forecast for time t plus 1, okay, capital T plus 1 up to t plus 9, and this is the uncertainty associated with my forecast. So what I'm saying is that the true value, okay, if I take the actual return series, which I'll be able to get from test 1, the true value I'm saying is going to lie somewhere within this interval. Okay, so there's some uncertainty related to my point forecast. This is a point forecast. Then around that, I create an interval to indicate that although I have made this forecast, I'm not very sure about it. Okay, for example, this darker shaded region, I'm 95% sure that the actual value of the return series will lie somewhere within this band. Okay, with 95% confidence, or there's a 0.95 probability that the actual value of the return series will lie within this band. Okay. Then for the 80% confidence interval, again, I'm saying that this is my forecast. These are my point forecasts for 9 steps ahead. But again, I'm not too confident about this. Okay, it's not 100% accurate. There could be some portion of this data that I could not forecast. Okay, so one thing that you need to note is any forecast error, it doesn't mean you're making a mistake in the forecast. Okay, it just means that there's some part of your data maybe which you cannot forecast, which is simply unforecastable. So this band here, these two bands, they just capture the uncertainty associated with your forecast. So this lighter band here you're saying that this is my point forecast for 9 steps ahead, but I'm not too sure about it. There's some uncertainty about it. So the true value of the return series for the remaining period, okay, for the remaining quarters, it's going to lie somewhere within this larger band with 80% confidence, or with a probability of 0.80. Is it clearer now?
Yes, ma'am. And ma'am, the line that we have got straight, it is only because the forecast has predicted
the
the same
same.
value,
Yeah.
but it might be fluctuating as well.
Yeah, it could be, for example, if you had used some other data set, then it might have had a different pattern. Here, there's no variation at all. Okay, so basically, our model is not very good. That's what you would have understood from this forecast itself.
Yes, ma'am.
Then let's do another thing. Let's compare, or let's generate the other types of forecasts and then also plot the test data and see what the actual data looks like and what are the other benchmark forecasts that we can use. Okay, so first let's just create, I'm going to call this F2 for the mean forecast. Okay, so here I'm using the average method. So here my forecasts are going to be equal to the average or the mean of the train 1 data set. Okay. Oh, sorry. Here I have to use the command mean f. Okay. So my variable, sorry, my model is b mod 3. Okay. And here I want to forecast again 9 steps ahead. So let me just generate this. D mod 3 equals 9. Okay, let me just see if I'm able to plot this or if something went wrong. No, something is wrong here. Let me just check. Oh, sorry, I cannot use the model itself, instead I have to specify, since it's going to take the mean of the data that I've used to generate or to model, so I have to specify that it's train 1. Okay. So let me just edit this command here. Okay, so this is the mean forecast, all right. So here you can see that the forecast that has been generated, it's equal to the mean of this train 1 data set. Okay, so all the observations that were there in train 1, the mean of that is equal to this, somewhere here, 3 point something. Okay. So let's just generate the rest of the forecast, okay, the random walk or the naive forecast. This again is the confidence interval associated with the forecast. Okay. So here I'll just use the command naive. Again, you have to specify train 1. Okay. Since it's going to use the last observed value, if you put the name of the model, it will just, since this is the Arima model, it won't be able to pick up the value of the last observation. Okay. So let's just run this command. We'll plot it all together later. Okay. So this is the naive forecast. I'll also plot the seasonal naive forecast. Okay, just so that you all can see what it looks like. Okay, for this again you need to use the actual data set. So we'll forecast 9 periods ahead again. Okay. Then what are the other methods? Yeah, just this. Okay, there's also another one. Let's plot this and then we'll discuss the other one. Okay. So let's plot all our forecasts that we've got so far. So first the forecast from our model itself. So when you're plotting, it will be helpful if you just name the series that you're plotting. Okay. So this is from Arima, I think 011, right? Okay, and set prediction interval. This is called a prediction interval or confidence interval. In R, it's called a prediction interval. Okay, so set that to false and then close the bracket. Okay, see, if you notice here, when I didn't put or when I didn't close the bracket, R is prompting me that there's something missing here. Okay, so whenever you're making an error in your commands, R will generally prompt you with a cross here. Okay, so then you can fix it and proceed. Okay, let's see. So what I'm trying to do now is plot all these forecasts, the forecast from my model plus the benchmark forecast in the same graph. Again, I'll put prediction interval false, okay? Because if I don't specify this, then it will show the prediction interval and that will overlap with the other forecasts, so I won't be able to see them. Okay. R is telling me that there's something wrong here. Let's see. This time I'll choose the naive one. Okay, so I missed a comma here, so that's why I think showing. And then we'll just plot the seasonal naive forecast also. So I'll run all these commands together now. Okay, I didn't type this properly, I think. Seasonal and I don't think I generated this. Let's see. So if you look closely at this graph, I'll just zoom in. So this one here is the mean forecast, okay, at about 3 point something. Then, but I don't know why it's not showing the rest. Yeah, I didn't specify the rest of it. So let me just specify the rest so that the entire legend appears on there. I'm just giving my graph a name.
Ma'am, shouldn't we do it in the autoplot command only?
Sorry. Shouldn't it be?
Ma'am, I was asking, shouldn't we do this in the plot command, like you are doing in the F4 seasonal command?
Oh, I think my entire thing just disappeared. Let me just go back. Autoplot. What was I doing before this? I think whatever I typed till now is gone, right?
Only the autoplot command.
Okay, let me just do this again. Oh wait, let me try and open up my other file and then copy from there. Okay, I'm just copying this just to save time since we're running out of time. Just copy this into this window. Here, instead of this whole thing, I'll just type F2 mean, right? Yeah, that one. You can do it directly without So I'll just run this set of commands and then we'll be able to see it. So here, if you look at this, this is the mean forecast. Okay. Then I think this dark blue line, I think it's still showing the prediction interval. So let me remove that. This is not auto Arima, it's Arima 011. So I'll just edit that. So let's just run this again and see. Yeah, now you can see it without the prediction intervals. So this is the mean forecast. Then this is the naive one, your random walk forecast. So basically it's just setting it to the last observed value. So all the forecasts are related to 2018 Q4 here. Okay? So the same value which was there for 2018 Q4, that same value is being repeated into the future for all the forecasts, 9-step ahead forecasts. Then this is the seasonal live forecast. It actually seems to be doing a decent job compared to our model also. Okay, so maybe there was some seasonality which we could not actually detect and exploit in the model. Okay. Then if you look at this one here, the dark blue line, okay, so that is related to our Arima model which we fit. Okay, so the rest of them are the benchmark forecasts, and this particular one is our Arima model. So it's a straight line, no variation at all. So basically we haven't done a very good job of forecasting, especially this portion. There seems to be some sort of a break in the time series. Okay. Now again, just to help you compare, what you can do is plot F1, which is the forecast from your model. Okay, I'm just putting it as Arima model for now. Okay, compare that with the actual test data. Okay, so the actual data from 2019 Q1 onwards. Okay, so let's just run this command and see. Test data. Plot. Okay, I don't know why there's an issue, but I don't know if I specified that test one is time series data. Let me just try specifying that it's time series data and then see. Okay, it does recognize that it's time series, but I don't know why it's not running the command. Okay, I'll correct the script and I'll stop for now, but you can compare your actual forecast from your model with the actual data. Okay? It should generally work if you do it this way. I don't know why it's, sorry, this is auto layer. Okay? That's probably why it went wrong. Yeah, okay, so here you will be able to see it. So this is the actual data which is showing that seasonal pattern that we saw from the seasonal naive forecast, and this is the forecast from our model. So clearly we have not done very well. Okay, so maybe it's a feature of this particular data that we've used. Maybe Arima models don't suit the data, or maybe the time series is too small. Okay, we are modeling using 39 observations. Now I had done this entire exercise using the entire data set. So the in-sample forecasts, if you look at it, are much, much better. They actually mimic this sort of pattern more closely compared to the splitting the sample and then leaving out some part and carrying out of sample forecasting. So you might encounter these sort of problems when you're modeling. So just be a little careful, okay? Try and use a larger data set and make sure that you seasonally adjust your data, that the seasonal adjustment, or if you want to model using the seasonal pattern, then you could fit the Arima models, okay? So you can do any of these things. I'll share this script with some comments, okay? By probably tomorrow afternoon, I'll share it with you all. Do you all have another class after this?
No, ma'am.
Can't
Not
hear.
today, ma'am.
No, okay. Then just bear with me for a couple of minutes. I'll give you a few quick instructions for your assignment, okay? We've finished everything. The only thing left is forecast accuracy. We'll discuss that in the next class. We don't have enough time for that. Okay? So today we'll stop here, but just a few quick pointers for your assignment. When you're actually analyzing data, try and use a large data set. Okay? 100 observations or more is good. Try not to keep it below 100. Okay? Then if you're using annual data, the seasonal effects get averaged out, so you need not carry out seasonal adjustment. So don't waste your time doing that if you're working with annual data. Okay? But generally, just because of that, don't switch to annual data now. It's just one simple command for seasonal adjustment. Okay? So it will not take much effort. And monthly data, quarterly data will be better for things like Arima modeling. Okay? Or more, what do you say, high frequency data. Annual data is low frequency data. Okay? Then when it comes to variables like GDP, then consumption, investment, and so on, try and make sure that you are using real variables and not nominal variables. Okay, so you might need to deflate your time series if you have chosen a nominal variable like nominal GDP. Then make sure you deflate it and use real variables. Okay, so you can deflate using CPI or GDP deflator. Okay, so you'll find all this data again from the same websites that I had shared with you all, same links. So make sure you deflate the data and then use it. Then another problem that you might encounter is structural breaks in your data. Okay, so if you're using a very long data set, or if you have data pertaining to the last few years, for example, 2019 was an odd year, right, for almost everyone and everything. So that might stand out and there might be a break there, although it will be a couple of observations. Even if you're using monthly data or quarterly data, it will be a few observations, but still there might be a break in the data. Okay? At this point of time, since we haven't learned how to deal with structural breaks, how to test for them and so on, so you will ignore that. Okay, but you might have structural breaks in your data. Once you learn about that, of course you'll factor it in, but at this point of time you need to ignore it. Okay, then structural breaks might show up as positive results for unit root test. For example, if there's a structural break in your data but it's actually stationary, the time series, if you run any unit root test, the test might tell you that the data is non-stationary when it's actually stationary. And this is because of the structural break, okay? Only because of that. So that can happen. But since you're not dealing with structural breaks, so you haven't learned how to deal with them at this point, you will just use the unit root test result as it is. Okay. So these are things to note. So even though your time series might be looking stationary or like it's non-stationary, if you factor in the structural breaks, you will be able to understand your results. Okay? Then when you're doing this entire empirical exercise with the data, okay, what I've instructed you is make sure that you create a, a zip file which has a Word document with your analysis. Okay? Then you need to share your data set with me. So make sure you include an Excel or CSV file with your data. Okay? and also your R script. So these three things should be there in the zip file, and then save all these documents. For example, the Excel sheet, Word document, everything should be saved with your roll number, okay, so that I can refer to that and compare whenever I'm running your script and so on. Then when you're doing the data analysis, okay, you need not write long stories, keep it as simple as possible. Okay, nobody wants to know about the history of Box Jenkins and so on. Okay, that's not what I'm looking for. I'm just looking to see whether you've understood these concepts of stationarity, how to actually model data using Arima modeling and so on. Okay, analyze data using Arima models. So that's the only thing I'm interested in. So keep it very simple and precise. For example, you'll say, I carried out this test. You need not state you need not write the statement, but you can just write ADF test. This is the null hypothesis. What is your conclusion from the test? Reject or fail to reject. You can write that. Okay, and what is your conclusion? Is it stationary or non-stationary? Then if it comes to the modeling part, make sure that you at least do 3 models, okay, or estimate 3 models on your own before you fall back on auto Arima. Okay, so don't go straight to auto Arima. Instead, try at least 3 times before you fall back on auto Arima and choose that command. Okay, then make sure that you comment on things like the ACF, PACF, why you chose that particular AR order, why you began with that, and why you began with that particular MA order. Then if you're using Sarima, you'll mention that there's a lag, significant spike at lag 4 for quarterly data. That's why you use Sarima and so on. Okay, so your identification process, you'll outline it clearly. Then when it comes to the model, again, the way that I have discussed, which coefficients are significant. Okay, you will write that down. Okay, put the t-value also. Then you will also comment on the AIC. Okay, whether since your target should be to minimize the AIC, how did you select the model? It has the minimum value of AIC, which is this number. Okay, that's what you'll put in. Then your graphs. If it comes to graphs, for example, if I want to save this graph, many of you probably know this already. What you can do is go to this option, export, save as image or save as PDF, copy to clipboard. You can use any of these options and save your graph. Okay? Then just to look at it a little more closely, you can use this command, zoom. Okay? Then to save your script itself, you'll save it this way. Go to this icon here. I've already given it a name, but if you hadn't saved it earlier, then it would have opened up a little box where you're asked to give a name to the script and you save it according to whatever name you want. So here I've asked you to save it according to your roll number. So you need to do that. Okay. So any other doubts or queries?
Ma'am, please just check the data that we are supposed to work for the assignment, because as per the instructions, it's a little doubtful that we have chosen the right thing or not.
Okay. Let me just see. I think it should be fine. I don't see. So far, except for this, she has changed her data set now. Okay,
Ma'am, my data timeline is from 1960 to 2020. Rashijan, 8th
okay,
number.
here. So how
No,
many
ma'am, below
observations?
this, final consumption.
Can you repeat the timeline?
Ma'am, it's from 1960 to 2020.
Okay. So you're looking at final consumption expenditure. So one thing you need to do is deflate, okay, or use, if you have current USD, just go directly to that data set and download it. Don't sit and deflate it yourself. Then 1960 to 2020, it should be fine, but there will be structural breaks, all right? So keep that in mind when you're doing your analysis. for now, ignore it and go ahead. Or if you know exactly when the structural break is taking place, then you can go ahead and, what do you say? Split your sample according to that, like how they do in the Chow test. If you have studied it before, you'll understand. So if you know the breakpoint precisely, then you can split your sample if you have enough observations, run both. But at this stage, I don't think it's really necessary. Just go ahead and estimate only one model, okay? Later on, once you've learned about structural breaks and so on, you can do all those things. For now, I'm just interested in the Arima modeling and stationarity, all those things.
Yes, ma'am.
The others, I'll have to go through it a little more closely. For example, this person, Samida, definitely there are going to be a lot of structural breaks here. Okay? And she's taking annual data. So it will be interesting for sure, but there will be structural breaks. Even this. Okay? Foreign exchange reserves from 1950 to 2020. Okay, so if you remember the whole crisis, near crisis, which happened around 1990, okay, there was a huge dip in our foreign exchange reserves. I don't think we had enough. After that, we've come to some 3 odd, I don't know, it's some huge amount today. Okay, so there's definitely going to be a huge jump here. So there might be problems with this data set again. So choose a little carefully. Think about what you're doing, what you want to do, and don't go in for annual data if you can help it. Okay.
Even exchange rates would be like that. No? I
Yes.
see 2-3 exchange rates here.
Yeah, but
There
I
will
think
be
if they're
jumps.
using monthly data, it should still be okay. See, there's a trade-off. When you choose annual data, there are advantages like you get a longer time series for variables like this. Then you don't have to deal with seasonal patterns. But the trade-off is that there will be structural breaks. There will be other issues with it.
Ma'am, one generic doubt. If you're using data like, let's say, GDP or CPI,
Yes.
you get information both as index as well as the nominal value. Let's say GDP, like, you also get the rate of growth, whatever. So some of these things already, you don't have to adjust the data, right? You can straight look at the GDP rates and go with that
Yes.
data.
The thing is, if you look at only GDP, for example, if you take real GDP, generally there'll be a trend and it will be non-stationary, the data. But if you take the growth rate, it's very likely to be stationary. That's the only difference. So you will not have to do any further manipulation in the case of growth rates. So you all can do all these things and simplify your work if you want. Okay, any other doubts or questions? Okay, so wish you all the best. I think that's it from my side. Keep it as simple as possible, and you need not use all these commands that we have used here. Okay, pick and choose only the most necessary ones, and you need not go about it in the same detailed way or anything like that. Do it in your own way. You need not name it mod 1. You can choose your own name as long as it makes sense to you. Okay, and that's it
Yes,
from my
ma'am.
side.
Ma'am, either could you please share the file or the codes above RPI command?
RBI.
RPI, ma'am. The commands which you shared today. In
Okay.
that there
Yes,
was.
yes. I'll be sharing this entire script with some comments so that.
Okay, ma'am. Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Okay, so I'm just doing this. I'm running this command. And and then I'll just plot it here, okay, just so you all can see what the problem might have been with our data. Okay. So here, can you all see this? This is the trend up to this point, probably 2015. After that, there's a whole change in the intercept over here.
Ma'am,
Okay.
your screen has stopped presenting.
Oh, sorry. Let me just see. Okay, only the two of you are there, but anyway, I'll just show you. So I just ran the seasonal adjustment command on the return series as it was. Okay, and if you look at the graph here, once I plotted the graph, what you'll notice is there's this break in the trend here, okay, around 2015. That is what this graph is telling me. So somewhere there was probably a structural break, and I have ignored that in my entire modeling exercise, and that's why my forecasts are not very great. Okay, so if you all encounter a similar problem, don't worry too much about it. If your forecasts don't look fantastic or anything, don't worry about it. Just go ahead and do the assignment. Okay, you're not going to get marks. I'm not going to compare forecasts and so on. I'm just interested in what each person is doing, whether they're able to do it correctly or not. Okay? So that's it from my side. Thank you.
Thank you, ma'am.